Um, Now I'm going to continue with applications of hypothesis test, and the strategy, the procedure that we are going to be following is going to be identical to what we have done in confidence intervals. First, I'm going to concentrate on the case of X being normal distributed, the population being normal, and the variance is known. And as you know, I call this the unrealistic case. I have explained why this is unrealistic before, but this is going to be, since it's going to be an exercise, it's going to be a good starting point. Then we are going to relax this assumption that variance is known. And then we are going to talk about not test on the mean, but test on the variance from a normal distribution. And then we are going to talk about finally on the population, test on the population proportion parameter. All right. So we have X normal distributed and variance is known, and case one is going to be a two-tailed hypothesis test. HT, I'm going to be using this abbreviation. So as I explained previously, in this case, the structure of the hypothesis test will be like this. Mu is equal to some given mu zero, and it's not equal to mu zero. And the test statistic that we are going to be using, and what does test statistic mean? Once we construct a hypothesis test, we need an estimator, a statistic to check the validity of either those hypotheses. So whether we are going to check whether our test statistic fall in the acceptance region or in the critical region. So the test statistic that we would be using is, after we collect the sample, we take X bar value, but actually we just convert transform the X bar value to a standardized form. And in order to do that, we subtract the X bar value from mu zero. Why do we do that? Because the philosophy of hypothesis test is that we, at the beginning, take H0 to be true. And since the null hypothesis is taken to be true, then mu is equal to mu zero. Therefore, X bar, the expected value of X bar, is assumed to be equal to the hypothesized value of the population parameter, which is equal to mu zero. So this is the expectation under the null hypothesis being true case. And we are going to divide this by the standard error of X bar. And since sigma is given here, variance is known, sigma square is known, we put sigma here, and square root of n is the square root of sample size of n. And this Z0 statistic is going to be standardized normal distributed with 0 mean and 1 standard deviation. Now, when and if alpha value significance level is given, then we use fixed significance level approach, and we use alpha to compute the z alpha or z alpha over 2 value. And what does z alpha over 2 correspond to? Z alpha over 2 value is the value of this z statistic, standardized normal distributed random variable, for which the right-hand side probability from that value to plus infinity is going to be equal to alpha over 2. Such that since it's a symmetric distribution, when you also have the alpha over 2 probability here, or the area here, the sum of all of these two areas is going to be equal to alpha. So the region between minus z alpha over 2 and z alpha over 2 is going to be equal to 1 minus alpha value. So once we determine the z alpha over 2 given alpha, we check whether this test statistic is greater than this value, actually the absolute value of that value. Why? Because we check whether z is greater than this one or smaller than this one. In other words, the absolute value of z0, we check whether it's going to be greater than z alpha over 2. Being the absolute value of z0, this test statistic greater than z alpha over 2 means that z0 is somewhere here. And in this case, we reject the null hypothesis H0, and we reach a strong conclusion. Otherwise, we fail to reject H0, null hypothesis, and what we obtain is a weak conclusion. And if you recall from the previous lecture, we have also at the p-value approach. In this approach, alpha value is not given here, right? No alpha value here. Instead of that, we directly just put the z0 value here and also minus z0 value here, and we compute the corresponding probabilities and add them together. And since they are again symmetric to each other, just computing one-tailed probability and multiplying 2 is sufficient. And how is this computed? Note that this area A is going to be equal to 1 minus, which 1 is the total probability under this curve, 1 minus cumulative distribution, normal cumulative distribution function evaluated at absolute value of Z0. So 1 minus the rest of this region here. So this area is going to be 1 minus in absolute values. Note that it's going to be in absolute values because Z0 might have been here also. But in both cases, we take this value. So it's going to be 1 minus cumulative distribution, normal cumulative distribution function evaluated at absolute value of 0 times 2. And times 2 comes from because we have these two tails corresponding to that extreme value. And the p-value is going to be equal to 2 times A. So this is going to be the idea. So our p-value is going to be reported at 2 times A. Now that was case 1. Case 2 is going to be the one-tailed version of this hypothesis test. Now the alternative hypothesis, note that now it changes into mu is greater than mu 0. Well, there's going to be also another case, is case 2, which is going to be mu smaller than mu 0. It's going to be that's why it's 2A, one of the one-tailed hypothesis. So in fixed significance level approach, the only difference compared to this one, again an alpha value is going to be given. The only difference is going to be, this time we are not going to find the Z alpha over 2, but we are directly going to find the Z alpha value because we are only interested in the right-hand side tail here. We don't care about any boundaries here. So once you find the Z alpha value, you again compute the very same test statistic, this one, and we check whether Z0 is greater than Z alpha over 2 or not. So here, this region is going to be the rejection or critical region here, right? Whereas this region is going to be from this Z alpha value to minus infinity is going to be what we call acceptance region. Of course, when I say acceptance, I do not mean accept the H0 hypothesis. This is just the name given to this region. So if your Z0 value falls anywhere here, we are going to reject the null hypothesis in favor of the alternative one. And if Z0 value falls anywhere here, we say we are not going to be able to reject the H0 mu is equal to mu 0 hypothesis. And when it comes to p-value, it's a very similar approach. We put the Z0 value here and we find that this tail probability. Note that since it's a one-tailed hypothesis test, the resulting value is not going to be multiplied by 2 because extremeness. Go back to the definition of the p-value. The probability that you are going to obtain an extreme value or a value as extreme as Z0 under the condition that null hypothesis is true. In this case, extremeness corresponds to only one side here, this tail here. Therefore, p-value is going to be simply this area. And since this area is equal to 1 minus normal cumulative distribution function evaluated at 0, 1 minus this region here, right? This is going to be equal to p-value. Well, for one-tailed hypothesis test, where the alternative hypothesis given as mu is smaller than mu 0, note that this is smaller than, although it seems to be there is a less than or equal to, it seems actually it's just less than sign. The very same thing is employed, but this time it's just going to be on the left-hand side. So in fixed significant level approach, we are searching for the Z value, which is on the left-hand side. So it's going to be Z alpha value, but we are going to be putting a negative value to find the limiting value here. So this area is going to be equal to alpha. So if your Z0 value is smaller than that value in this region, this is going to be our critical region. This is going to be acceptance region. I'm not going to repeat all the things. And when it comes to p-value, it's going to be the area on the left tail here. So therefore, p-value is going to be directly equal to normal cumulative distribution function evaluated at Z0 value. Let's solve a question related with this topic. All right. So the question is, again, let me give a scenario related with the question. Let's say that our company produces roads, and the length of these roads is pretty important in terms of quality control. And we would like to test whether the population mean of the roads is equal to 50 centimeters or not. And we would like to test this hypothesis at a significance level of 0.05. So, and also sigma value is also given. Sigma is equal to 2 centimeters. So here actually, you're not clearly see it, is 2 centimeters. So the hypothesis test here will be constructed in this form. Mu, and here mu will represent the mean length of the roads that we manufacture, is equal to 50 centimeters. And the alternative hypothesis, it's not equal to 50 centimeters. And now we are going to, I have not written it here, but we are going to assume that X is normal distributed, or it's going to be given us. Then once we construct this hypothesis test, we can collect specimen, and let's leave this part to the end. Actually, let's behave as if we haven't collected the specimen yet. So what we are going to do is, we are just going to use the fixed significance level approach to come up with the limits. So let me write here, because it's going to be a little bit of a long question. So let me change this pointer color. Okay, that one is better. All right. So first, significance, fixed significance level approach. Alpha is given 0.005. Since this is a two-sided test, I'm going to be interested in alpha over 2, 0.0025, right? Then I need the z values of 0.025. This is going to be equal to, if you check in your textbook, it's going to be 1.96. This 1.96 is going to be the upper critical value, and minus 1.96 is going to be the lower critical value. So what we are going to do is, we are going to check whether our test statistic Z0, actually the absolute value of Z0, is greater than Z0.025, which is equal to 1.96 or not. So now to compute Z0, we take these with a sample consisting of 25 specimen, randomly selected specimen, and we compute the test statistic. Test statistic here, actually, in a real situation, of course, the X values of X1, X2 to X25, all of them will be given to you, or you would have measured each of them and you would obtain these values. From these values, you compute X bar value. So I just took a quick, I just bypassed this step, and this is going to be mu over sigma over square root of, and note that mu here is the suggested value here, the one in the null hypothesis. So it should be mu 0 actually. Note that this is equal to mu 0. So this is going to be equal to 51.3 minus, because we believe that the null hypothesis is true, minus over 2 over square root of 25. When we do this calculation, it's going to be equal to 1.3 over 2 over 5. Yes. And the result is going to be equal to 3.25. And here we can see that 3.25, you can take the absolute value, still 3.25. This is greater than 1.96. So it is in the critical region. The test statistic I'll come up with is in the critical region. Therefore, we say that, and this formal conclusion is also important, there is sufficient evidence to suggest that, please note that in actual questions, do not say we reject H0, we accept H1, things like that. Do not deal with H0. Please write the result explicitly to suggest that mean length or mean road length is not equal to 50 centimeters. And note that this is going to be a strong conclusion. Here, please note that strong does not mean without any probability of error. There is probability of type 1 error, which is equal to 0.05 here. The type 1 error probability is this one. But I've explained previously why this is a strong conclusion, because a single observation is sufficient to reject an equality hypothesis. And note that this is an inequality hypothesis. Although there is burden of proof lies in showing that this is valid. Since this is an inequality, we can show that inequality holds, but on the other hand, we can never exactly show that an equality will hold. All right, so this is the fixed significance level approach. Now I'm going to solve the very same question using confidence interval approach that we have employed in the previous chapter. All right, and then I'm going to compare those two. B is going to be confidence interval approach. So confidence interval approach is basically find X bar value, then subtract and add the same margin here. And this is going to be square root of 2, is going to be smaller X bar plus Z alpha over 2 is equal to 1 minus alpha. That is the idea. So this is going to be basically equal to probability of X bar is equal to 51.3 minus Z alpha over 2 is 1.96 and sigma is 2 and square root of n is 25 smaller equal mu smaller equal 51.3 plus the very same value here is going to be actually equal to, let me write the value, 0.874. This is going to be equal to 0.95. So if we go one more step, what we obtain is this is going to be 52.8 is going to be equal to 0.95. So we can say that as a conclusion here, 50 point mu is going to be between 50.52 and 52.8, or let's write it that way. Mu is going to be in this interval. Mu is in this interval at a 95% confidence level. So this is the formal conclusion of the confidence interval approach. Now you may say, what's the confidence interval approach got to do with the hypothesis test approach? Actually, we can use this interval, right? The interval that we have found for mu to test this hypothesis. And the test is very simple. We test whether suppose the hypothesized mu value lies in this region or not. It does not. Actually, it falls here on the left-hand side of this region. Therefore, we are going to say that mu is equal to 50 centimeters does not lie in 50.52, 52.98 region. Hence, the previous result that I written about, there is sufficient evidence to reject that mu is equal to 50 centimeters. All the result again. But the way to connect the confidence approach to the hypothesis test lies in this statement here. The hypothesized value, we are going to check whether the hypothesized value in the null hypothesis, mu is equal to 50 centimeters, does it lie in the determined confidence interval or not. If it's in the determined confidence interval, we are going to say we cannot reject that the mu is equal to 50 centimeter hypothesis. If it does not lie here, in just like this case, we reject the null hypothesis. So one may actually liken, or one may compare two processes in this fashion in a real axis. If this is our real axis. Then the hypothesized value of 50 is here. Then, now, the upper and lower values, now I'm talking about the fixed significance level approach. Actually, this region is going to be, and this region is going to be equal to Z alpha over 2 sigma over square root of n. And this value is going to be equal to, I have computed previously, but let me compute it again. It's going to be 1 over 96 times 2 over square root of 5. It's going to be equal to 0.784. So therefore, this value is going to be equal to 49.22, something like this. And this one is going to be 50.78. So in hypothesis test, what we do here, let me get rid of this one. We have an X bar value, and here X bar value is 51.3 meters. We check whether this X bar value falls in this range or not. Actually, X bar value is here. It's going to be 51 point. I think it's a little bit more on the left-hand side. I shouldn't erase this, but that's, I think, okay. It's going to be somewhere here, I guess. X bar is equal to 51.3, whereas mu is equal to this one. This is the hypothesized value, and this is what the X bar has come into, has been realized. Now, in confidence interval, what we do is we draw a confidence interval around X bar. So let me put it that way. So this is the bounds or the hypothesis test, and we check whether X bar is in this region or not. It's not. And in the confidence interval approach, we determine a confidence interval for X bar. And that confidence interval was 50.2, the lower limit, or 50.52, I'm sorry. I again erase this one. This is the lower critical value, lower confidence bound, which is equal to 50.5, and the upper bound is going to be 52.1 or 0. So here I'm going to show it with those shaded lines to show that this is the confidence interval. And when it comes to, I'm very sorry, it's going to be here. Not this one. All right. So in the confidence interval approach, the way to conduct an hypothesis test is to check whether the hypothesized value lies in this confidence interval region. So note that the two methods will always agree, right? If mu is inside this region, then X bar, so if mu is inside the confidence interval, X bar will be also in the acceptance region. This is the idea between those two. The hypothesis test constructs a region bound, taken the hypothesized value at the origin and check whether X bar falls in the acceptance region, whereas the confidence interval approach takes the sample mean in the origin and determines a confidence interval around the sample mean, and then you may check whether the hypothesized value mu0 in the null hypothesis falls in that confidence interval or not. And both methods should always agree. They should, both methods should always agree. If they do not, then you are probably, you are making a mistake. All right. So this one is also over. Now we had actually another method, which is p-value. And in p-value method, we just forget about this alpha. We don't care about this, and it doesn't need to be given to us. We simply find Z0 value. And Z0 value here is found to be equal to 3.25. And since this is a two-sided test, let's actually go back to our previous slide. All right, is it this one? Yes, this one I'm talking about. I'm sorry, this one. So the p-value approach of two-sided test, actually p-value is going to be equal to this area plus this area. So it's going to be the normal cumulative distribution function evaluated at the absolute value of Z0, 1 minus that value multiplied by 2. So I'm just going to be applying this very same thing. So p-value is going to be equal to 1 minus 2 times 1 minus 3.25 in absolute values. Well, actually, it's already positive, so there's nothing. That's so. This is going to be the cumulative distribution function evaluated at 3.0. So it's 3.25 is this value is 0.9994 if you check your textbook. 1 minus this value multiplied by 2 is going to be equal to a pretty much small value. It's actually, as you can see, it's like 0.1%. Is that? Yes. If you multiply by 100, it's going to be 0.1. And what does p-value mean? Let's remember what this is. And all right, probability of an observation, probability of an sample, a sample with an x-bar value as extreme as the current sample, given that H0 mu is equal to 50 centimeters, is actually equal to 0.1%. It's a very low probability. So assuming that mu0 is 50 centimeters, it is only with 1 in 1,000 we are going to obtain a sample with a sample statistics as extreme as this current one. Therefore, we do not think that this mu0 is equal to 50 centimeters will hold. And note that here p-value is p-value, which is found as 0.0012, is actually much smaller than the alpha value, which is taken to be equal to 0.05. Therefore, actually, if you consider as 0.05, then you can again reject the null hypothesis. But as I said earlier, p-values, you don't need to come up with a conclusion when you report p-values, but usually people do. So there is either, although you use the p-value in your calculations, there is usually a significance level that is in your mind somewhere, which is equal to 0.05. So if a small value of p-value, if a p-value much smaller than 0.05 is obtained, or 0.01, you usually report that this is a very small value. So this is a very highly significant finding. That so it is highly significant finding that mu is not equal to 50 centimeters. This is a pretty much highly significant finding. All right. Now I'm going to talk about an extension of the same question. And this actually, as I said, is a long question. Test whether the mean road length may exceed 50 centimeters, again given the same population standard deviation, and again at 0.05 significance level. Here actually you probably cannot see it, but it says mu is going to exceed, the mean road length will exceed 2 centimeters. So here, maybe we are interested in, we are going to use these roads in some construction. And the very important thing is the population mean should not exceed 2 centimeters for some reason, right? Well, if it's smaller than 2 centimeters, that's okay. So we are especially interested whether our population mean will exceed 2 centimeters or not. Now the construction of the hypothesis will be in this manner. because we are only interested in the alternative hypothesis that mu is going to be greater than, I'm sorry, why that 2 centimeter come from? It's 50 centimeters, of course. And we are going to test this hypothesis at 0.05, the very same thing. So again, we are going to collect some samples and we are going to check. Let's say that we have taken the same sample, right? But usually before that, in fixed significance level approach, what do we do? A fixed significance level approach. First, we find the critical Z value. So alpha is equal to 0.05. Since this is a one-sided test, we would be only interested in Z 0.05 value, which is going to be equal to 1.65. And note that since this is a right side, actually one-sided test, but mu is greater than 50 centimeters, we will be interested in the positive Z value. And how do I find this? Actually, you may go back here. When the alternative hypothesis is mu is greater than mu0, then we would be interested in positive Z alpha value. If we were interested in mu, the alternative hypothesis that mu is smaller than mu0, then we would be interested Z is smaller than minus Z alpha value. And this, you don't need to memorize any of these actually in your textbook. But more than that, the logic actually dictates mu is great. The way to test this mu is great, this alternative hypothesis would be to compare the Z0 value, the test statistic, with a boundary value. And that boundary value should be a positive value because we are talking about a mu value greater than the hypothesized one. Anyway, so what we do here is that, so we obtain the same sample. Assume that, again, where is our sample? We collect a sample of 25 specimens are collected, and X bar is found out to be 51.3 centimeters. Just for the sake of not complicating the question. So once we obtain this, again, we now compute the test statistic, and note that it's going to be identical to the previous one because the null hypothesis is identical. And again, that's the important thing about fixed significance level approach. The test statistic is totally identical because in test statistic, we use the null hypothesis properties. And null hypothesis is not related with the alternative hypothesis, since it's only a point, is an equality here, and therefore mu is not going to change. So this is going to be, again, our standard deviation is 2 over square root of 25, the very same value, which was 3.25. So therefore, we are going to be comparing this value with this value, and as you can see, there is nothing changes. So the way I usually show it by this way, Z0 value, which is equal to 3.25, is greater than Z0.05, which is equal to 1.65. Therefore, we are going to again come up with the same result. There is sufficient evidence to reject that population mean rod length is equal to 50 centimeters. There is sufficient, but not only that, and mean is greater than 50 centimeters. I think this part is a little bit necessary to reject that and suggest that. I think this part may be a little bit unnecessary. If you like, you can get rid of this part. There is sufficient evidence. All right, this part I think is maybe better. There is sufficient evidence to suggest that mean population rod length is greater than 50 centimeters. Since we are not talking about a single point here, we do not verify any hypothesis. Note that the alternative hypothesis, the inequality, is actually a rejection of the null hypothesis. And this is going to be, again, a strong conclusion. Now, one important point, the way I constructed the question is actually just for the sake of coming up with an exercise. Once you construct an hypothesis and take a sample and apply that hypothesis test, then you never change your hypothesis and do the same calculations. That would be actually, that would be invalid from a statistical point of view. Because once you construct an hypothesis test and apply on a sample, then you have some information on that sample, right? And you may either realizing on purpose or maybe without realizing, accidentally, you may use that information in your new hypothesis. That's not something that you should do, because then you would violate the random sample assumption. Because the sample should be random means that it should be independent from all the previous observations and also from the calculations and what I think, and also from the hypothesis itself, right? Because when once I take a sample and after finding the X bar value, if I come up with the hypothesis, then the sample observations would not be independent from my calculations, and that would violate one of the hypotheses, and the results would be unreliable. Okay, now let's talk about the second approach, which is confidence interval. Should I call it? I think I should call it B. Now, in confidence interval, there is a very subtle point we should consider. Well, probably you may you probably realize that since we had a two-sided hypothesis test, then a confidence interval was need to be found. But when it comes to a one-sided hypothesis test, a confidence bound is to be found. So it's going to be either on the lower side or on the upper side, there's going to be a bound, and the other bound will go to infinity. However, here the problem is which bound is going to be taken. And believe me, in exams in the previous years, I have seen in many occasions that many students are confused about that part. So is it going to be left-hand side, the bound, is it going to be on the left-hand side, or is it going to be on the right-hand side? And actually, I would like to try both of them to see that one of them only will work. Okay, so here let me first write the correct answer. Lower bound should be used. And of course, we are entitled to say why. Let me try to show you. Now, when I obtain a lower bound, it's going to be something like this. Let's say that this is our lower bound, and it's going to be plus infinity. And we are going to say that mu is going to be in this region. And then what we are going to check is whether actually if the mu value is equal to suggested mu zero value, which is equal to, let's also write the suggested value. Mu zero is equal to 50 centimeters. Actually, let me write the hypothesis test here again. Mu is greater than 50 centimeters. All right. We test whether mu is equal to 50 centimeters falls somewhere here. For instance, let's say that it falls here. Now, that means that the lower bound will be on the left-hand side of the suggested hypothesized mu value. So this region here will cover the hypothesized value. So here we do not reject the null hypothesis. So this part is going to be not rejecting H0. I said actually do not say not rejecting H0, right? The full hypothesis, but now for the sake of just concentrating on a different aspect, this region why I write H0. Okay, let's say that lower bound is found to be here, again on the very same axis. This time, it's going to be this region that mu is supposed to be. However, mu zero is hypothesized to be here, right? Mu value is here. So this case would be rejecting H0. But let's also write here rejecting H0 in favor of H1. Why do I say in favor of H1? Because H1 says that mu is greater than 50 centimeters. So here we reject H0. So we say that 50 centimeters is not in that interval. What about the alternative hypothesis? What did it say? It say it may be some value greater than 50. Is it consistent? Is this confidence interval consistent with alternative hypothesis? Yes, it is. That's a great thing. And this one is also compatible with the null hypothesis. And if something is compatible with the null hypothesis, you stop there. Now, if we had used the upper bound, and this is the correct bound. If we had used an upper bound, then what different type of answers would we have obtained? One answer would have been like this. I'm again using the same axis, right? So it's going to be from minus infinity. This is the upper bound. And let's say that still 50 centimeters is here. So we have found one option would be, one possible outcome would be upper bound would be here on the right-hand side of 50 centimeters. So therefore, the mu would have been here in this part. And as you can see, it includes the mu is equal to 50 centimeters. So here we would not reject H0. So this outcome is compatible with null hypothesis. That's okay. Now the problem lies in this one. If your upper bound is found to be here, then it means that mu value is supposed to be in that region due to the confidence interval approach. Now, what does that correspond to in terms of our hypothesis? Could we say this result is the case? Well, this interval does not contain 50 centimeters. That's great. So this seems to be, we reject H0. But note that we are also given an H1 value, an alternative hypothesis. So we have to reject H0 in favor of H1. The problem is, can we say that? Because this confidence bound and this interval which goes from which comes from minus infinity and goes until upper bound does not contain the null hypothesis value of 50 centimeter, but also does not contain any values suggested by the alternative hypothesis. So here, this outcome does not correspond to anything that's been tested by our hypothesis test architecture. Therefore, here we cannot use this bound. This would be an incorrect bound to test this hypothesis, these two hypotheses, I may say. The correct one would be lower bound. So be careful with that. One very simple way of, let me say, not memorizing, but keeping in mind which approach to use, maybe when you see an alternative hypothesis in this fashion, mu is greater than 50 centimeters, find the lower bound. So it's going to be like lower bound, mu is greater than that value. So it's going to be greater than that value kind of thing. But actually, it's just a kind of just reminding you about that practical approach, reminding you about that association between the confidence bounds and the hypothesis test, the one-sided hypothesis test. The correct rationale lies in this approach. Anyway, so here for this specific question, we are going to be using an lower bound here. And the lower bound, therefore, if you go back to the part related with the lower bounds in one-sided hypothesis, this is going to be 51.3, which is the sample mean, 1.65, which is that alpha value is going to be 2 over square root of 25. This value is smaller than this value with 0.95. Therefore, here we can find this to be equal to mu is greater than a lower bound of 50.64 centimeters with a probability of 95. So note that this says that it's going to be from the mu is going to lie in the interval. Actually, it's not an interval, but in the is going to be bounded on the left-hand side by 50.64. So mu will lie here at 95% significance level. And since this does not contain mu is equal to mu 0 is equal to 50 centimeters, then we are going to reject the null hypothesis, and we are going to say that we have evidence to support that mu is greater than 50 centimeters. So when it comes to the last topic, which is going to be p-value approach, it's going to be simply equal to, if we go back here in p-value approach, p-value is going to be the right-hand side probability. Is shown with 1 minus cumulative distribution function related as 0. So it's going to be 1 minus cumulative distribution function of 3.25, which is 1 minus 0.9994, which is going to be equal to 0.0006. I repeat again, this is not the way that we use hypothesis testing. What I mean is, I have started with a equality, with a two-sided hypothesis test, and using the same sample, I have employed a one-sided test. We do not do that. You are not justified in doing that. If you are going to conduct a one-sided hypothesis test, you do it at the very beginning. You conduct it. So depending on the value of X bar, you cannot change the hypothesis test. And something like the following is also not allowed here. For instance, you say that at the beginning mu is equal to 50 centimeters as the null hypothesis. After you obtain the X bar value, now you say, okay, let me try mu is equal to 51 centimeters. You are not also allowed to do that. You conduct your hypothesis test you construct your hypothesis test at the beginning without having information about the sample that you are going to collect.